So good morning to everyone. Hope everybody is fit, healthy, and in good spirits. I'm just trying as we're going through to do the register, so please, there are still one or two people, according to my reckoning, that are missing. So I'll go through and we'll see if we can catch up on those people a little later on. So good morning. I hope that today we're going to get the chance to do some lab work. As you can see from the presentation, we are actually going to be looking at capacitors, and that is the next part of our section before we'll make the start after the Christmas break on waves and wave activities. So hopefully we're going to see now that that is part of the final run-in, the final part of everything before we look at the final sections. I've said to you, and I hope that most of you managed to read the classroom comment, that you will need to make some notes during the middle towards the end of the presentation. And I am going to ask you to produce a graph, which from the data that we're going to do on screen, and you're going to then submit that into the Google Classroom. So please make sure you've got a pen, paper, ruler, pencil available to help you to then go through the correct data. I do have a copy of that data. I don't think you'll be able to see it just yet on here, which is the set of data I recorded earlier today. So, making a start. If there are any questions, please, I would like you to, as usual, make the comments in the comment box and the chat line so that I can see them and I can try and answer them for you as we are proceeding through the lesson. So I'm sorry, I'm just got Schoolsoft running and it's slowing my system down a little. So should be 32. And we are about 29. So a couple of people still missing. Okay, let's have a look. Start on the presentation. If any of you have questions, please, you can put your hand up. You can ask if you wish to. Just let me know as and when you need the questions. Questions have come in. Can you use Google Sheets? I would prefer, please, that you use a simple sheet of paper. Again, if I just show you, which you can't see, I've done this on a single sheet of paper with the values at the top and the graph at the bottom. It's only 10 values. It's fairly straightforward, and I will show you exactly what needs to be done. So please, I would prefer that it's a hand-drawn or hand-produced graph rather than Google Sheet. Right. There we go. So today we're going to look at these wonderful devices. And again, I've got some just here that I can hold up and show to you. These are typical capacitors, very different to the device that you can see on screen at the moment, but we'll have a look at these and see how and what they are. So we're going to look at three things. Probably today we'll just get through what is capacitance. We'll go on tomorrow to then talk about how we work with capacitors, how we discharge them, and what the energy stored in a capacitor looks like, though we will mention that slightly during today's lesson. Now, in essence, a capacitor is a device that stores charge. It consists of two conductors, and these conductors, very similar in nature to something like this, which you can, well, you can't see, but you can see where it's supposed to be. If this were a metal plate, this were a metal plate, and there's a layer of insulation in between them. Now, the whole thing started around the 1750s when a gentleman called Ewald Georg connected an electrostatic generator. You can see this wonderful device that's illustrated in there from 1700s. And it gives you an idea of the type of devices and equipment that was available during that sort of time. And this is basically a friction device, and the device itself simply allows you to connect into a system such that trying to get my mouse in the right place, just here, a charge is being generated, and this rather antiquated piece of apparatus allowed the charge to be transferred into this jar over here. And what Georg, or Ewald Georg, found was that if he placed a wire into a jar containing a liquid, it was possible to transfer this charge. And indeed, when he came to look at the charge, he found even after the charge generator was detached or disconnected, he was still able to get a charge and got an electric shock. He had discovered that the jar could store charge. Now, how did that work? Well, sometime after that, at the University of Leiden, they developed a process whereby they took an ordinary jar and placed a layer of silver foil or of aluminium inside that jar, then wrapped another layer outside the jar, and they were able to transfer electrical energy into that jar. And we have a device at school which does this for us, which allows us to transfer the charges through these electrical connectors into the jar. And these jars are called Leyden jars, and we have one or two of these at school. Different designs, slightly different materials, but the principle is exactly the same. When we make a connection between each of these jars, we connect them together just as we would in a battery. And indeed, this group of jars was called a battery of Leyden jars. And this battery comes from something similar to the medical terminology, which we use to describe a battery of soldiers is a group of soldiers. So this battery of Leyden jars actually allowed us to transfer charge, take stored charge inside each of these batteries and transfer it to another place. And he was able, and the University of Leyden, they were able to connect these batteries together to increase the amount of charge stored inside a system. So what is a capacitor? Well, any device that stored charge using conductors separated by an insulating layer. And I've said those are the devices that you can see there. I have these devices just here, which if I put them in the right place, you should be able to see them. So these are similar types of devices. I move them into my face so you can see whereabouts they are. These provide the same thing that we use in modern day capacitors. Interestingly, the first units of capacitance were measured in what they called jars. So the first measure was 1 jar of electrical charge was the unit they described. So if they had in the previous diagram 6 jars, that was 6 jars of capacitance. Modern day capacitors don't use that unit. We use the farad, as you'll see in, I think, the next diagram. Capacity is the, capacitance is the ability of a body to hold an electrical charge. It can also be described as the amount of electrical charge for a given voltage. And I'll show you exactly what that means in a few moments. Now, the standard unit, as I've said, is the farad, named after Michael Faraday, who was the first person to develop capacitors effective enough for physical usage and for practical applications. And he measured the effects of different variables, the size of the plates, the materials they made them from, and so on. And he was the first person able to demonstrate that. Now you'll see here the first diagram, a symbol for a capacitor. And we represent that as 2 plates with an insulating layer in between them. Now I have one question for you. Why can we connect a battery directly over this capacitor? If I were to take an electrical circuit, and let's just say I have a battery somewhere here, or I did have on my desk, but of course it's gone. So let's just imagine this as a battery. I take my battery and connect my capacitor to it. Why can I do that? Why is that allowed in electrical theory, that I can take a capacitor, connect it to a battery, and the circuit is still allowed? Why is that?
The charge is moved around.
You can, but what is important? There's one important reason why we can do that.
Well, the insulator within the capacitor.
Great, well said. It's exactly that point. There is an insulating layer between these 2 metal plates. So if I take my capacitor just here and place it onto my battery, there is actually no physical connection between the top and the bottom. I'm trying to get this to stay in place. So inside here, there is a physical barrier, insulating barrier. Now, 1 farad is the capacitance when a voltage of 1 volt appears across a capacitor's plates when a charge of 1 coulomb is stored. Now, you'll see that that charge, 1 coulomb, is a pretty large charge. We will talk about much, much smaller values than 1 coulomb, but we will see where that comes from. Thank you, Oscar. I will keep an eye on that. Sorry, I'm just checking my record. Yes, okay. Now, I'm not quite sure that if any of you just noticed that there was a message saying that this uses Flash, Adobe Flash materials. From the 1st of January, my understanding is that Flash will no longer be supported. Whether it will still be used in presentations, I'm not sure. But I will need to see how I use these presentations after the 1st of January. So slight aside, a capacitor is a device that stores energy in an electrical field between 2 parallel plates. So let's have a look at this. What we've got inside here is actually 2 parallel sheets of metal that are, as you can see, wrapped around in a continuous loop. Separating these 2 from each other is what we call a dielectric. And this dielectric is what keeps that metal plate separate from this metal plate. And the top of these and the bottom of these will be connected to the leads. So there is only 1 lead out, but if we trace the track of these, they will go all the way to the center just here. And as you can see, inside the outer casing is a rolled up pair of metal sheets. Now, an experiment that I wanted to do for you, and which we tend to do in class, I'll set that up to show you a video of that in a couple of moments. But we can view that and see just how that capacitor works. So if we go in theory, what we've now got is 1 sheet of metal, a 2nd sheet of metal, and an insulator in between them. And to charge a capacitor, what we need to do is look at the distribution of electrons. And what we can see in here is that the electrons in this circuit, when I connect a battery, are equally distributed. So now I've got in this circuit a battery over here, which is going to supply for us electrons into this circuit. Now, before I turn the switch on, the electrons are distributed evenly all around this plate, this circuit. So the electrons are not moving, They are stationary. There's an equal number on the top and the bottom plate. If I now switch on this circuit, so I can now cause the electrons to travel around the circuit, what you can see is the electrons have flowed from the positive plate into the battery, through the battery, and onto the negative plate. And in theory, what has happened is the electrons have gone from this plate to this plate, but they haven't traveled through the insulating material. They've traveled through this electrical circuit onto this plate just here. Now, if we again consider this circuit, as the electrons collect on one plate and leave the other, they build up charge. Eventually, though, this will balance and all of the electrons, near enough, are on one plate and there are no electrons on the other plate. So if I now do one thing and I supply a device into this circuit, this device can measure the charge that's flowing between these two plates. And this is a meter showing us we have 1.5 volts across here, and we can turn on the circuit. Now what will happen is the electrons will leave this plate, they will travel in the opposite direction and travel back to the top plate. So now we have 0 voltage across that plate. Let's go back and look at that again. So if I now connect my voltmeter across the plates, I see there is a voltage of 1.5 volts, very much the same as the voltage that was on the battery. Turn on the circuit, the electrons travel around the circuit and they're deposited on the positive plate. Now we have no voltage across this capacitor. Let me see if I can pull the video for you. Just bear with me one moment. It's a 4-minute video that I wish to run for you. I think I should be able to do this. Can you hear?
We don't hear anything.
Okay. Okay. I can describe what is happening on here. Let me just pause this. Right. Turn down the volume on my other computer. Right, what we've got here in this illustration is a simple bin liner. If I just go back. If you can do, I think the reason is because one of you was first into the meeting, and so I am not the owner of the meeting, so to speak. If you can do that, then do go ahead, please. Do you want to try it, Charlie? I'll close this one of mine.
These are capacitors, and they're used in electrical circuits to store charge. They're crucial components in things like defibrillators, computers, and mobile phones. And as you can see, they come in a variety of shapes and sizes. But they've all got two of these connecting leads, and these are connected on the inside to two thin sheets of metal, which we call plates, separated by a thin sheet of insulating material, which we call a dielectric. You can introduce the topic of capacitors to your students using this large-scale model. What I've got here is two bits of foil for the plates, separated by this thin sheet of plastic that I've cut from a bin bag for the dielectric. The whole thing's resting on this other sheet of plastic to keep it insulated from the bench. You can charge this capacitor up using an extra high tension power supply. I'm going to connect the positive terminal to the top plate, and I've got the bottom plate connected via this center 0 microammeter to the negative terminal. Now, before you use this in class, it's important to determine the maximum voltage the capacitor can take before it breaks down. And we do this by turning the power supply on and gradually increasing the voltage until you hear these sparks, and then turning the voltage down until just before the sparks start. And here I'm using about 900 volts. I'm just going to turn the power off and discharge by completing the circuit, and give you a quick note about safety. When the capacitor's connected to the power supply and it's turned on, you mustn't touch any exposed bits of metal. However, when the power supply is off, it's perfectly safe. So now it's ready to use in class. I usually begin by pointing out the various components and showing how it's connected, and asking my students if we've got a complete circuit. I then ask them to predict what they're going to see on the ammeter when I turn the power supply on.
Can you pause it, Charlie? Thank you. As he just said to you, I would have shown you this in class. We have all this apparatus. I have the bin bag capacitor, this device over here set up, and we have this thing called the microammeter. What he just said is, can you predict what will happen on the ammeter when we connect the electricity? So what do you think you will see on this ammeter when the current flows to the capacitor? Just type in a response if you can, please. Just tell me what you think you will see. Anybody? Will the ammeter stay as it is? I don't think it'll go bonkers. That's not a very scientific. It will increase constantly, or what? You're correct. It will increase, Oscar. But interesting. Will stay at a constant value. You are correct, but I think it's interesting to see. Can you run it again, Charlie, now, please?
So let's see what happens when I turn the power on. You can see the ammeter kick to the left. I'm going to turn the power off now and discharge. And the ammeter kicked in the opposite direction this time. So what's going on? Well, when I turn the power supply on, it pulls electrons off the top plate, leaving it positively charged, and pushes electrons onto the bottom plate, leaving it negatively charged. And it's this flow of charge that gives us the initial reading on the ammeter. Once the potential difference between these two plates is the same as the potential difference of the power supply, the current stops. When I discharge the capacitor, electrons move off the bottom plate and onto the top plate. And once again, it's this flow of charge that gives us the current. The current stops when the bottom plate and the top plate are no longer charged, so the potential difference between them is zero. This is a lovely setup to illustrate the construction of a capacitor and demonstrate how it stores charge. But there is one other thing you can do with it. You can show what happens to a capacitor when the voltage is too high.
Watch this. This is now the interesting bit. Okay, thank you, Charlie. Thanks. So that gives you an idea of what a capacitor is. And all I am trying to show you in the, let's get back to the presentation as I close the, in this circuit, you saw the voltage measure the current flowed only when the electrical circuit was turned on. I just go back one step here, turn it on. Sorry, turn it on. The current flows in one direction. When I turn it off or connect this voltmeter, the current flows back in the opposite direction. So you've seen that now in a real live lab demonstration. Okay, Oscar, I take your point. It has gone bonkers, but it's not quite the science terminology that I tend to like to use, but good observation. So let's get back to a real student situation, what we are looking at now. And we describe a capacitor as something that stores charge. So what does this mean? Well, it means when a capacitor is charged, electrons move off one plate onto the other, and overall charge is transferred. So now I've got an uncharged capacitor, equal number of electrons on each plate. Over this side, I've charged my capacitor by putting a battery in the circuit, so all of the electrons have moved onto this plate. This becomes negative, this becomes positive. And the capacitor itself remains neutral because the total charge on here is still equal to the total charge on here. It's just that the charge has transferred from one plate onto the other plate. So we've now done work. Moving the electrons onto one side means that we've transferred energy. And this capacitor stores what we call electrical potential energy. So if we go back to one of our much earlier slides when we were talking about energy and power, this is a different type of potential energy to gravitational potential energy. But it's the same thing. It's the movement, it's the position of the electrons which cause them to have energy. Because when we connect those two leads together, and I can just do that with, where's my capacitor? Just here. If this capacitor were charged, try and get you so you can see it. If this capacitor just here were charged and I connect those two leads together, the charge will transfer round this circuit and balance on both plates. So the charge moves around this circuit. That is part of the working system for a capacitor. So what do I want you to do? Right, now is the time for you to start to get prepared. What we're going to do is have a look at this circuit, and you can see now we have two complete circuits just here. If the connector is connected on this side, we can connect to a battery and we can vary the voltage in that battery from 1 to 10 volts. Once we've done that, we can transfer the switch over to this side, and the circuit is again made on this side. So our electrons that we've transferred from here will now transfer onto this circuit. And when we make the circuit, the electrons will transfer through this Coulomb meter and back to the other plate, so balancing out again. That's the process we call discharging. So I'll start it, I'll just show you this with 10 volts. So we've now connected a 10 volt battery on here. We've charged this battery, and if I now click measure, I can measure the amount of charge that was stored on that battery. So if we now click this, what I've now done is taken all of the charge and stored it in this circuit. So what I need to do, and what you are going to do now, we'll do it with all 10 sets of readings. So I'll reset now, starting with 1 right through to 10 volts. You need to now record the Coulomb value. This value is in micro coulombs, just so that you are aware. This is not a 90 coulomb, this is micro coulombs passing through this meter. So let's select our first value. Let's charge the capacitor with 1 volt and now measure the value. And we get now 10.8 microcoulombs flowing through our circuit. So now we've got the first measurements. I will now go through and do each of these, reset the meter, charge the capacitor with 2 volts and measure. We now get 18.3. So reset again, charge with 3 volts and measure. We now get 29.1. So let's reset, charge with 4 volts, measure. Now move to reset, 5 volts, measure. Reset, 6 volts. Seven volts. Eight volts. Measure. Nine volts. Measure. And finally, 10 volts. So charge the battery, then we discharge through the Coulomb meter. 95.6. So you should now have 10 sets of readings that will give you the values that we need for our graph. So I hope that all of you have managed to note those. What was the 7th reading? 7 volts was 67.0. Thank you. Okay, good. So now, having done that, what I would now like to do is let's have a look and see exactly what it is that you have just done. My results are on screen, okay? So how did the voltage affect the amount of charge stored on this Coulomb meter? So we did 2 things. We applied a voltage, we measured the charge on that capacitor. What happened to the value of the capacitor? The capacitor, did we change the capacitor at all? Anybody? No. It stayed the same. So when we increased the voltage, we saw a change in the current, the charge on this meter. So we kept the capacitor constant and increased the voltage. So let's have a look and see. Now, your readings were not the same as these, so they're not the ones I want you to use. But what I do want you to do is now do a charge against voltage graph for this capacitor. Remember, please, your graph needs to have a title. So you need to have the title of your graph. You need to have a set of axes. So I'm just making a note. You need to have a set of axes, look and see where, what, which ones would be the correct value for you to have. You also need to be able to see which type would give you the correct results. You need to include the units. As I said to you, the units for charge on this axis, microcoulombs. The units for this axis, volts. Those are the correct solutions. So you have now charge, microcoulombs, voltage in volts. And that, oops, I'll go back to this one just here. This is the graph that you need now to draw. So your values need to fit onto this graph. There is the title, there is the units and charge, there is the axes that you need to use. So that is what you are going to draw. Now, I'll give you, we'll finish in 5 minutes or so, but I just want to give you 3 questions that we need to go through first of all. We have here a relationship that charge increased with voltage. We kept the capacitance constant, so we could work out any one of these values if we know 2 of the others. So I'm going to ask you the first question. What charge is stored on a parallel plate capacitor if the device has a capacitance of 10 nanofarads, N standing here for 10 to the power minus, anybody 10 to the power minus, the N should give you a clue. -9, correct? So we've got 10 times 10 to the -9. The voltage is 5 volts. So please work out the charge of your capacitor if you know its value and its voltage. So just work that out for me quickly, please. So let's see some answers. I want to see a representation before I move on. Good. So we have appropriate answers. Where's my cursor? There. We have appropriate answers. The values being 10 times 10 to the -9 times by 5, which gives us then 50 times 10 to the -9, which equals 5 times 10 to the -8. Be careful, Charlie. You are correct to use the units, but just be careful. It's 50 times 10 to the -9 coulombs. So 5 times 10 to the -8 equivalent to 50 times 10 to the -9. No problem. We all do. So second one, this time, calculate the voltage across an unknown capacitor is 15 volts. It's discharged onto a Coulomb meter and the charge is 4.5 times 10 to the -3. What is the capacitance of this device? So capacitance is now charge divided by voltage. Let's see if we can calculate this one. Good. So we're getting some good answers here. Again, how do we calculate? Well, we first need the equation. Great. We need the values, 4.5 times 10 to the -3. So we've now got, oops, wrong one. 3 times 10 to the -4, or 0.3 millifarads. Now, I have in here, again, I'm not sure. My other PC is just turned off for the moment. This is a developer's set of capacitors. You can probably see they all look very similar, but there are lots of different values. 10 microfarads, 22, 100, 220, 100 nanofarads, 33 nanofarads, and so on. And you'll see these change all throughout different activities. So I have this as one set, and I have a second set just here. I'm not sure if these are the same. Yes, they are. But you can see inside here. Not sure if you can see these. Yeah, you should be able to see them. We've got two sets of capacitors, each having these different values. Now you have to be very, very careful in construction because they look very similar, but they actually store significantly different amounts of charge, which means the voltage they can deliver. And we'll look at that in tomorrow's lesson when we start to go through some of the things to do with the uses of capacitors and how they can be used effectively. One of the most important that we do use is the use of the defibrillator, which is something some of you may have heard of in medical spheres, how we calculate charge. And we can use it then for activating the heart by delivering a very large charge, high voltage, in a very short period of time, which of course then supplies energy to the heart, stimulates the beating to revive a person. So we have, for the final question here, we have a voltage of 12 volts, which is now sufficient for us to conclude today's lesson. As I've said to you, please, can you now go ahead, do the graph? I'd like you to, if some of you need to go off and have a break beforehand, please do that, but try and get it to me by about 1 o'clock today so that I have this. I just need a copy pasted into the classroom and we're done for today. Okay, any questions? Anything that you need me to help you with or questions need answering, please just ask. Okay, so I'll sign off for now and see you for the lesson tomorrow.
Thank you. Goodbye. Have a good day.
Thank you. You too. Have a good day.
Bye.
Bye.
Thank you.
Bye.
Bye-bye.